Swayam Prabha. Digital India. Educated India.
Okay, so good morning, day number 5, 1 week, and we are getting into wrapping up the descriptions about what Raman spectroscopy is. Then we'll go into the surface properties, and we will probably today begin already talking about operando things, and certainly during next week you will get all the operando that you need. Okay, fine. So yesterday we were talking about different things on Raman spectroscopy, and another thing that is also possible to do with Raman systems is to make maps. They typically come connected to a microscope, and this allows you, looking within the spatial resolution of optical microscopes, what is happening in your system. You can get chemical images. At the different coordinates, you can get different information. Usually, nowadays, most of the equipment come with a motorized stage, so that you can really define the maps. You don't have to go one by one, but it will be made automatically. And you can make line maps, surface maps, many things. And the information can be very interesting. This, for instance, is a case which is basically a carbon fiber coated by silicon carbide. And basically, you have this fiber, they cut it, and then they look a map about a section of this carbon fiber. And basically, the idea is, for instance, well, you are looking here in this 70 microns long distance, 75. And you can measure, for instance, along a single line and see what information you get, or even you can analyze all this area. So first of all, we can look at Raman spectra at different coordinates along this carbon fiber and the coating with silicon carbide. With your eyes, probably you cannot tell where you have the carbon and where you have the silicon carbide. And of course, this is the outside. This is just garbage and junk from the outside. But where is the transition? Well, with the Raman spectra, you will see the Raman bands of the carbon fiber, 16 and 1300, which is like the typical D and G band of a carbon species. So at different positions, you will essentially get that. Until at a given moment, you get something different, which is this spectrum here, at about 20 microns in this axis, which is basically characteristic of the silicon carbide. Now, interestingly, if you keep on moving along the line, it means not only here where you see this silicon carbide coating, but you move outside, like there out of the material, you see Raman bands of carbon again. But this is carbon mainly from cutting the pieces into that you get debris all over, and then this is just like some kind of residual carbon fiber particles that occur at the surface. What you can also do is to make a Raman map in the area, and you can look at individual spectra at every single point, or say, okay, because at each of these points I have the complete spectrum, what I can do is integrate the area of this 1600 Raman band that correspond to the carbon fiber. And what I can do is to map at each coordinate where I have taken a spectrum, what is the area of the Raman band of this carbon fiber that you are obtaining. So basically, this is what you get. When it goes from red to yellow to white, you are having more and more and more. So you can see basically that all of it is the carbon fiber, and down here, the Raman signal of carbon fiber goes down to 0, because there, which is at about these 20 microns that we saw before, is where you have the silicon carbide coating. You could make the reverse. You could integrate the Raman band of the silicon carbide, so this will be pretty much 0, and over here you will see the Raman band of silicon carbide. So mainly with Raman imaging, you can get this kind of information at different coordinates. And again, like we saw before, when you go out of the fiber and you're still measuring there, you will see a few bands of something, which again is carbon, but this is actually you see the debris out there. So these are like these particles from broken carbon fibers that remain at the outermost, beyond the outermost surface of this material. Another classical example is a diamond coating on, actually yesterday we were talking about this kind of coatings on graphene, which is associated with some kind of computer industry. So basically in this case you can have like a graphene coating, so you get the G band at 1600 of this carbon and the diamond, which is about 1300. So you can look at how well covered is this coating, so how well you get this diamond coating at the surface of this graphite. So this could be a kind of Raman mapping mainly associated with quality control. If you use a white light, and sorry, this is in Spanish, luz blanca means white light, basically what you see with the microscope is that, something grayish with white things, darker things, but you cannot really tell whether this is diamond or whether this is graphite, and anyhow the diamond is transparent, so even if the diamond on top of the graphite, you won't really see it that nicely. So you can look at this area, which is 40 by 40 microns, and then you can establish a grid. So like measure every micron. So you make a 40 by 40 grid, whatever, like 1600 spectra that you get there. And then you can look at the spectra at every single coordinate, or you can analyze the information. So third try, microscopes, imaging at a given coordinates, you can get spectra. So you can take a lot of spectra at a lot of coordinates. At each coordinate, you have a spectrum, like this one. And in this case, it was just a carbon fiber coated by silicon carbide. So depending on the coordinate, you will get a Raman spectrum of the carbon or of the silicon. Then you can plot things like that. But there is a lot of information within this spectra. If you want to visualize, if you want to make a map, a chemical image, you have to handle this spectra differently. So what you do is to say, okay, these two peaks correspond to the carbon fiber. So don't plot me a spectra at every position, which is very difficult to see, but illustrate with this the intensity of the area of the carbon fiber Raman band. And then you see where you have the carbon Raman bands with a lower or higher concentration or medium concentration, so it's more or less intense. Here you see that this is the end of the carbon fiber, and over here you have something different, which is the silicon carbide. And then outside of this carbon fiber, you get some debris of broken carbon fiber pieces, so you again see some Raman signal of carbon fibers, very weak, very random, very scattered, because this is not the material, it's just outside garbage, litter that you get out there. You could also look at the map and integrate the band associated with silicon carbide, so these things will be empty. And over here you will have a nice color telling that you have silicon carbide. So you can combine this kind of information. And the one case that I was commenting is about graphite covered with diamond. So diamond is covered on graphite layers for applications in computer industry, and you need a quality control. So you make these kind of Raman measurements, which is basically not research per se, but quality control, and you are monitoring what is happening there. So this is a 40 by 40 microns, and then you make a spectrum every micron, so you make a grid of 40 by 40, which is like 1600 spectra, and you see what you get. And what you get can be analyzed in many manners. You can look at 1600 Raman spectra and go crazy and say, okay, let us plot relevant information. Like for instance, what is the area of the Raman band of diamond at 1300? Okay, so this is it. It goes from very low to very high. So here you see, like you have maxima of diamonds at some position. So the coating of diamond on graphite in this 40 nanometer range is not homogeneous. You get an even distribution with more diamond here, very little diamond there. If you make a map of the Raman band of the graphite substrate, basically what you get is complementary. You see big amount of graphite in areas where you get very few diamond, and vice versa. So you can get the distribution. And if you want to go more into detail, what you can also look at the full width half maxima of the Raman band. So when a structure is very well defined, the Raman piece will be sharp, slender, elegant. And if it is ill-defined and defective, it will be shorter, broader, thick. So the peak width will tell you the quality of this material, for instance, the diamond. And in this case, the full width goes from smaller values to bigger values. And where do you get the smaller values? Here, which is in area where you have a higher concentration of diamond. Why? Because in that area you have more diamonds, is more developed, is better coated, is better defined, so you get a sharper Raman band. And the Raman band of diamond is very broad in this region, which is a region where you have very few diamond. Why? Because it's very incipient, very ill-defined, very defective. So you can see the coating, and you can also get structural information. Basically, you can plot anything out of your spectra. You can plot the relative intensity of one spectrum to the other. You can plot the absolute area. You can plot the peak width, and this will give you a lot of information. Or you can also monitor at the distribution. This is a very old, but this is telling you that, these things were made already a number of years ago. Of course, systems are a lot faster now, but for instance, there are like drugs mixing caffeine, cocaine, and amphetamine. You cannot buy this in the pharmacies, I told you. But illegally, people is doing that, and then the police is getting those things, and then they're making analysis. And when they're making analysis, you can see how these drugs are distributed. Caffeine has a characteristic Raman band over here, cocaine over there, amphetamines over there. You could look at that one, but it overlaps with that one. So when you want a map, you want to look at bands that do not interfere with each other. And then you can look at the area intensity of these bands within these pellets. And then you get a map of a pellet that is not very well made, because you get like distribution of cocaine with a big bunch over here, amphetamine over there, caffeine over there. So it's not very evenly distributed. So whoever made it, it's not only an illegal product, but it's also not very well mixed. But the same thing happens with the catalyst. You can make a pellet, you can put a catalyst, and you can use some molybdenum nitrate to diffuse within a pellet, a porous pellet, so that the liquid with the molybdenum precursor is being diffusing through the pore of this material, and then you can make a Raman map and get different coordinates and see how much is the amount of molybdenum that you have. In this case, because you have to quantify somehow, they were using the nitrite of the medium as an internal standard. So what we are plotting here is basically the intensity of molybdenum with respect with the intensity of the nitrate Raman band. And then you can observe areas where the molybdenum is. This is before impregnation. At the beginning, you get basically molybdenum within the periphery of this pellet, how it is progressively diffusing, that you already have something inside while it is still outside. And then at the end of the synthesis, 3 hours, molybdenum is homogeneously distributed within the pellet of this material. So you can monitor this element distribution just by using Raman spectroscopy. And a catalytic pellet is like a porous particle. And you can also use products with caffeine, which are legal, like aspirins. I don't know if here you say paracetamol or acetaminophen. How do you say in India for the headaches? Acetaminophen or paracetamol? Okay, so, like in Europe, because in the US they say acetaminophen. Okay. So this is a pellet that has a little bit of aspirin, caffeine, and paracetamol. And here you have a Raman band, where basically they are plotting the intensity of a Raman band characteristic of the aspirin, of the caffeine, and of the paracetamol, and they are always looking for a band that doesn't overlap or interfere with the other one. And quality control in this case is that when you make an aspirin, it must be evenly distributed. And in this case, you get like a high concentration of one thing, local maxima. This is very uneven. So this is a non-valid sample, while the other one is a valid sample. In this case, these are like medical pads that you put in the skin for treatments, or I don't know, even probably for nicotine people who take a patch, and then this is diffusing through the skin. So when you put these things that diffuse through your skin, you need that the medical component is evenly distributed through it, because if you put the pad and everything is concentrated here, maybe you get a reaction. But if you put the pad and everything is evenly distributed all over that area, then you will get the treatment effect and you don't get a reaction. You will also see that use it before May 2027 for the aspirins, for the paracetamol. Why is that? Because a molecule is a molecule, and it will probably never change. So say, come on, why should the medicine expire? And of course, the molecule, like a paracetamol molecule like this, it will not expire, but it has several configurations, several isomers, and the crystalline structure will affect on how efficiently it kills your headache. So basically what they are doing is that they are looking at the different conformations, and there is a polymorph which is efficient and another one which is not efficient. So you take it, I mean, it won't kill you, but it won't heal your headache either. So basically, they do that, and then they do the analysis through 1, 2, 3, 4, 5, 6, 7, 8 months. Still, the polymorph, which is efficient, remains abundant. But after 9 months, they observe that already the polymorph that is not active, it becomes dominant. So that means that you are taking paracetamol, but it's a polymorph that is not helping you. It's not damaging you, but it's not helping you. And of course, you cannot have a lot of paracetamol to get the right dose, because you take a lot of paracetamol, you get an hepatic failure, and then you die. So you have to take the right amount, and if it is expired, go and buy a new one, because that one is already not that efficient. Have you seen this sometime in the airports? They are very concerned, mainly because of the liquids, and then you go through it, and you have a liquid, throw it away, drink it out, but you may not go into it. Well, because there are a number of explosives that look like water, but they're explosives. Like, for instance, this is the case of UV-vis spectroscopy may not be very discriminating, because it has an absorption maximum at about 220. Imagine you could take a Raman spectrum with a laser at 220. Then you will get the strongest possible spectrum for a given concentration of this compound. Like we said yesterday, because of the resonance effect, because you're using just the wavelength at which this molecule absorbs. So it gets resonantly enhanced, and you trigger the Raman signal of this compound. If you were going to look at it at 240, okay, the resonance enhancement is no longer that special. You are already near resonance, but not really at resonance, so the spectra for the same concentration will be weaker. And if you stay like we typically do in most of the cases in off resonance, you will get whatever you get for this compound. Now, you can do something, taking advantage of what I said yesterday about resonance effect and amplification of the resonance. You can play and take Raman spectra at many wavelengths of excitation. Typically, you cannot do that with Raman systems that most of us buy, because basically you have 2, 3, 4 lasers. But there are continuous lasers where you can select the wavelength. And then you can do something which is very powerful, which is to take a spectra at 200, 220, 230, 40, 45, 40, at any wavelength, and see what is the Raman spectrum that you are obtaining exciting at a given wavelength. Now, what will be the outcome? Well, it's basically something like that. The spectrum of this HMX will be stronger when you are getting resonance, and will be weaker as you go away from the resonance frequency. And then you get something that looks very nice. And in this case, basically, what they are doing is looking at the solution of HMX. When you are making a spectrum at 220 excitation line, basically you are getting resonance. So for that concentration, you get a much stronger peak of this compound. And if you go away from that frequency, like 250, then you will get the standard spectrum of it. But you can see the effect of the resonance enhancement. The spectrum is the same, but it gets resonantly enhanced. At some wavelengths, for instance, you get like there is a maximum there at 220, you also get another maximum at 230, because another part of the molecule is absorbing at about 230. So when you get there, this part of the molecule gets resonantly enhanced. If you don't know those things, you can get confused. But if you know this and you use that information, you can get a lot more of a wealth of information from your spectra. Of course, having a Raman system with a continuous tunable laser is not something that everybody has. There are very few, but this is very good to make this kind of results, and visually it's also very attractive. Okay, confocal microscopy. How many people is acquainted with what is a confocality, a confocal microscopy study? But you have the word confocal. Okay, confocal is something which looks like magic to some extent, because it's the ability to be able to look inside a sample, but without cutting off the outer layers. Just basically you see inside, through it, and you can focus inside it. Is it doable? Yes. It's an optical trick. There is a technology to do that. It looks like magic, but it's real. And all the time magic occurs because of something as simple, conceptually, as a pinhole. Now you will see how it is like. And then you can focus at the desired spot, And this pinhole is what really it makes it work. So this is the concept of a confocal microscopy. If you're looking at the surface, basically the lens will take you to the detector and then you will see the image. But if you want to go and focus inside the sample, how do you make it? How do you focus inside the sample? Well, you just move the sample so that the focus point is no longer here, but inside the sample. Okay. But then everything gets blurred. Yes, of course, do not panic. When you make confocality, there is something else added in the system, which is this, the pinhole. And the pinhole is a pinhole, just an opaque thing with a little pinhole. And why is it helping you to make confocal imaging? Well, I want to look at something which is here in the middle layer of it. Okay. Because the system is focused there, what is at this focal point will go through the lens, through the pinhole, to the detector. Anything which is closer to the sample, above your point, will go through it, but then it will not go through the pinhole, it will be a stop here, and doesn't get to the detector. And what is beyond the focal point will also crash and will not go through the pinhole into the detector. So you are basically looking inside a material as long as it has a reasonable degree of transparency, of course, and basically you are killing things which are before and after. It's like seeing my skin without seeing my shirt, without taking my shirt off. So you go do confocal to see my skin through this. And then you cancel the signal from it, and then you get to see the skin inside. And of course, you are not dealing with centimeters. Usually you are doing that with microns. You are doing that for research. You are not going to do like Superman that looks through this wall, what is in that room, in the other room, or in, no. You not do that, you only do with microns, but it will be, you remember, you know who is Superman? Do you? Come on, say yes, no. This is an easy question. Do you know Superman? Okay, you know that they say he has X-ray vision? It's wrong, he has confocal vision. Because X-ray vision will go through all the building outside. They say X-ray, but this is confocal. So, but it's special. In Krypton planet it works like that, but over here we are limited to a few microns. And also the way it works, this confocality, is that you can see through it at one point, but we are talking about maps. And you can go point by point by point and generate what is happening at the given level. Experimentally, that will be time consuming. So people is coming out with intelligent ideas. First of all, on the left side, you have the way it works with the microscope systems, because you get the light from one side, a mirror that takes the light onto the sample, you illuminate inside it, and then you go back and through the pinhole, only what is at the plane of focus that you are looking for is what gets to your detector. But this is for one point, because you have a pinhole. So what they do in the microscopes is that instead of a microscope, you get like a rotating disc full of pinholes. And because it is rotating, it's basically describing a confocal plane. So anything which is in this confocal plane will go through the filter to the detector, and anything which is above or below this confocal plane will be stopped by this disc, so that you can get the confocal image on a given surface through this kind of technology. This is typically used in biology, in fluorescence microscopy, to observe things. Like, for instance, this is a neuron from a mouse, and you are trying to look into this neuron, which is marked with a fluorescent molecule, with a normal microscope, and yeah, you see the fluorescence, but everything is blurred because of the scattering of light. So you don't really know where is actually the fluorescent marker on these neurons. However, if you make a confocal, all this light from above and below is cancelled. And all you get is only the light from the plane where you are focusing, where you are interested, where you have your fluorescent label. And then the same image without and with confocality looks very different. This is just confocal microscopy for fluorescence. But you can also do the same thing with Raman. And you can look, for instance, inside a cell without killing the cell. We are dealing with a few microns. And this is the realm of confocality, like a few microns. And then you can look at the cell. And you can look at the Raman band, for instance, beta-carotene. And the beta-carotene is located inside this vegetable cell. So up there you see how an old cell looks like, and down here how a young new cell looks like. Not a big difference with white light. But then you go to confocal Raman and look at the map of beta carotene inside the cell. Now, what do you observe? That the baby cell, basically the beta carotene is quite evenly distributed inside the cell with a local maximum, but that's it. The old cell has like a bimodal distribution, has like two areas with two local maxima. Why? Because this is an aging cell. It is preparing to do mitosis. It is preparing to split into two cells. It is split yet? No. Does it look old to you? No. But to the eyes of Raman, say, hey, the chemistry inside the cell is already changing. They are preparing to have like two nuclei. The beta carotene is already being distributed. So you are getting information on the physiology of a cell without killing it. So that is very interesting. And we were talking about drugs before. And you can also do information about drugs, how they go not only in the body, but also within the cell, in which part of the cell they concentrate. So there you have a distribution of I don't remember which drug it was, but basically you get a confocal Raman mapping within the cell, identifying how this drug that is assimilated by the cell doesn't go everywhere, but it has specific locations. And also you can even monitor how it is being degraded and metabolized. So this is important. This is biology. I show these things because confocality is coming from biology realm, but for us we are more dealing with materials. There was a classical example which was made by one of the Raman companies when they start selling the confocality, and it's basically a piece of plastic which is polyethylene covered with polypropylene. But you don't go from polyethylene to polypropylene like that. There is a progressive change. So like the amount of polyethylene is decreasing continuously, and in that region, you also have a progressive increase of polypropylene. So what they were doing is to look inside this plastic every 2 micrometers, 2, 4, 6, 8, 10, 12 micrometers, inside the material. And then what we could see is that inside the material, you were getting the Raman bands of the polypropylene. In the outermost layer, you get the Raman bands of the polyethylene, and in between, you can see that there is a linear combination of spectra. So like the polypropylene is becoming weaker, 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 and polyethylene is becoming stronger, 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 as you go from the surface to the core of this material, which is a nice demonstration. But if you were a smart scientist and you are going to look at the polyethylene to polypropylene profile in this sample, you will not do a confocal study getting into it. You will take a knife, you cut it, and then you look from the side. But this is a very simple case. So if you cut it and you look from the side, of course, you will get the same thing much faster, because one problem of confocality is that total intensity decreases. Because usually when you are using the microscope, when you focus here, you get this volume around it into your spectrometer. By doing confocality, the volume around the focal point is minimized, because anything that is above or below the focal point is cancelled. So that means that the volume that you probe when you are making confocal, well, the volume you probe is the same, but the volume that gets to the detector is filtered by the pinhole. And that means that less photons go to you. So you are much more accurate in space, indeed. You get rid of things which are above and below the focal point, certainly. But the total number of photons that get to you is lower. So the intensity of the signal is lower, so you get a weaker Raman signal. But, I mean, that's part of the deal. I mean, you trade off something and you're trading another thing. Now, you want to make a confocal microscopy. You have the microscope here in the air, you have the sample here, and the sample is not air, but between the microscope and your sample there is air, maybe a few millimeters or nearly touching, but there is air. Is it important that we are looking through air to a material? Because typically, I mean, you're looking from the microscope here in air to a sample here, and you focus on the surface. But now I want to focus inside. Can there be any problem if I try to look inside the solid? You know what is that? You know what happens when you put a stick in the water? It looks like something changes. Now, So there's this light refraction. So try imagine focusing inside the sample when all of a sudden you have that. But I have a beautiful microscope objective. Yes, but physics are the physics. And when you're going from air to this material, the refraction index changes. And then all your focusing things change. So they talk about the point spread function. When you are very close to the surface and you make focus here, this is okay, but this is the surface. And then you want to look inside, inside, and inside, okay. But when you look inside, your point, which was like this, now is like this. You go more inside and it's like this, more inside is like this. So you think that you're looking at 1 micron, and maybe down here you're looking at 10 microns. And also because you have all this kind of spreading of light, the collection is also not that efficient. So the deeper you go into it, the more inaccurate, the more distorted you are, and the less efficiently the signal goes back to you. So what do? I mean, the deeper I go, the more spread it is and the worse the signal comes back to me. Do we have a solution? Yes, we do. Well, here you have basically focusing, this is air, and this is the solid or liquid inside which you look like. And so things change. And there is a little distortion and a bigger distortion the deeper you go into it. And the way you handle that is because between your microscope and between your sample, you have air. And this air that you have there is giving you a lot of problems, a lot of headaches, because even the light that goes out doesn't typically go back to you, it's also lost out there, so everything is lost. When people is doing confocal microscopy, they have something in between. So the objective is not the typical objective, but there is oil. So these objectives are immersion objectives that go into a liquid that touches your sample and touches your microscope. So the microscope is no longer in air, it is in a liquid, with a refraction index which is very similar to the refraction index of the materials. Going from air to solid and liquids usually go from a refraction index of 1 to 1.5. So basically there is a commercial oil which is used to do that. And then it's either you do immersion in the same liquid or you use this oil, and then you avoid that problem. And then you can see inside without being full. So basically it's a commercial product. They sell many. And you put it between your sample and your objective. But the oil may affect the sample. No worries. They have like a few microns thick glasses that you put these micron glasses on top of your sample, the oil on top of this, and the microscope on top of it. So it's a kind of a sandwich layer. And that works. That works very well, because then all this point spread function, this loss of quality, is no longer there. And if you are looking at an spheric particle, I don't know what is in there, okay, but you can see that the spheric particle that with a good confocal system will look spherical, and you can look inside. If you have a bad confocal without oil, the spherical particle will look like elongated. Or even more dramatic here, this is like a PVC coated by polyethylene or something like that. So you can look at confocality, you look at it, and if you are using it correctly with the oil, you will look inside it and you can penetrate into it and measure one plastic, the core plastic, and the outside plastic very nicely and get a 3D image of this thing inside whatever matrix it is. But if you are not using the oil and you are having the point spread function, you will get these kind of things. The signal will no longer look with the right shape, it will be distorted, apparently, but because in reality the sample ends there, but it will appear it ends there because of the refraction. And the signal will be weaker and weaker. Here you see solid, here you see more porous, and here you can see that basically things kind of disappear. So if you're going to make confocal, you need this kind of, it's simple, but you have to use it. And we have been looking at those things for something that is not exactly catalysis, but I think it is also relevant. What happens when you are eating plastics? The other day I was showing you polyethylene terephthalate and the degradation of it and how it was affecting the microbiota in the stomach, in the intestines. So we did something similar with polylactic acid, and in this case we did essentially the same thing, looking at the plastic with the saliva of the mouth, with the acidic of the stomach, with the small intestine, and then with the colonic fermentation, taking samples and analyzing at every single stage. So they made all the biological part at the Food Science Institute, and we were looking at the Raman of this material. And basically, what we are observing is we were making a map at 60 positions. So you get like 60 spectra of this sample, original or in the oral phase or in the stomach phase. Basically, you see that the plastic is not changing because I have 60 spectra and it looks like only one. You hardly get any noise. Then when it goes to the intestine phase, you start to see some changes. Here is more apparent that some positions this band is weaker and stronger, so there are some changes. And then when you go to the colonic phase, you not only see changes, like for instance, these bands were more intense than that one, and now these bands are weaker than that one, so you do really change many things in this polylactic acid, but you also get a build-up of some broad Raman bands at about 1600. Now, this is telling you that there are some kind of carbon deposit or species growing on this plastic, something related with the physiology of our body. Here you have a blow-up of this. Basically, you see that these are carbon deposits there. Also, structural information is showing changes over there. And basically, looking at the relative intensity of the bands, you can see that from the fresh to the used sample, there is a change in the amorphicity, loss of semicrystallinity. And the most interesting is, okay, we see some carbon deposits. What are these carbon deposits exactly? So on the fresh sample, like oral phase, basically we made a confocal study. So 0 is the surface, minus 1, 2, 3 are the basements, and 1, 2, 3, 4 is upstairs, above the surface. So here you have some Raman bands associated with the plastic that do not change. The only one that really matters is this one, that is corresponding to the carbon species. We get no carbon species at the surface of this plastic in the oral phase. When it goes to the intestine, you see something, hardly any inside it under the surface, but mainly at the surface and above the surface. So that you get some increase of carbon species mainly at the surface and above, and slightly diffusing into. And during the colonic fermentation and intestinal phase, you see a lot more of these carbon deposits. So you can really see that many things are changing at the surface of this material. And also, between this phase and this phase, even these carbon species may look a little bit different. And what we did is to investigate a little bit more in detail. So what you can do is to, okay, and this is just, if you get like a small fracture on the surface, you see that inside the fracture, there's a big accumulation of carbon species, while the surface are still quite clean. Basically, we were looking at this region here. This is up in the surface, this is down in the cliff, and then again up in the surface. So you see that in the cracks, things accumulate, because the more broken a plastic is, the more attacked it is. But the interesting thing is that in the gastric phase, if you look at all the spectra and you get the standard deviation, things fluctuate around here, and the average deviation is this. And this is basically amorphous carbon. You are getting like amorphous carbon accumulating on the surface of the plastic. But during the intestines, the standard deviation, this is the average spectrum, and the standard deviation of these 60 spectra looks very different. It's very noisy, it looks like that, but this is already much more closer to protein Raman bands, amide group, and other things. So it's kind of indication that you are getting an incipient development of a biofilm. Something is growing there, bacteria or whatever. You cannot tell very accurately, but at the beginning of the digestion, like in the stomach, you accumulate carbons, and then bacteria and other things start to grow and thrive at the surface of this plastic. And you can see that in detail because of the confocal imaging at the surface of this material. This is not catalysis, true, but you can try to do these kind of things in catalytic materials. I couldn't find a good example, but examples will come anytime now, because you are dealing with shaped catalysts, you are dealing with pellets, you are dealing with porous materials of given shape, and you can do these kind of things. We want to do these things, and maybe next time I visit you, I can show you these kind of applications for catalysts. But this is something doable. That is something interesting. And of course, there was an effect in the genome and phylum. In this case, there was a significant increase of bifidobacterium, because polylactic acid is also very similar to many organic things. So actually, more than a decrease in the bacteria population in the stomach, there was an increase because they like it. polylactic is biodegradable, it has these ester groups, and life like eating ester groups. So in this case, different to the polyethylene terephthalate that was decreasing population, in this case, it was increasing population during 72 hours, and then everything went back to normal. Okay. Another aspect of spectroscopy is that I'm always talking about the laser, the sample, and the spectrum. But we need something here. We need a spectrometer. How does a spectrometer look like? Of course, you already know Raman's Raman system, and nowadays they are different, but the basic principles are the ones that Raman established in the system. So they look like this. For instance, we have a Renishaw, and basically the system is something like that. It may look complex, but basically the laser is coming here from behind the screen. There is a mirror, then laser goes here. This is like a beam expander that basically makes that the very thin laser becomes like a bigger laser, but very homogeneous, but thicker. And then there is one mirror. There is another mirror here that takes the laser into the microscope. So the laser goes through here into the microscope to the sample, illuminates the sample, collects the signal back, goes back to the spectrometer, and then things happen here so that only the Raman signal goes to the detector, and what is not Raman signal, the elastic scattering, is rejected. But the general concept is something like this, and now you will see the parts of it. The first thing you need is an excitation laser. Raman was using the sun, and the measurements were slow, were difficult, were very complex, and during the 40s and 50s, infrared spectroscopy became generalized. So while there was a lot of papers using Raman, after the 50s, the number of Raman papers decreased because infrared was much more easy, much more convenient. But then in the 80s, laser technology became very general, and then during the 80s, the number of Raman spectrometers rocketed, and then during the 90s and the 2000s, the technology of electronics was even better. So now Raman is taking all the field that was taken by infrared is being recovered by Raman. Not only because of the lasers, not only because of the quality of the detectors, but also for something very simple, how we measure a Raman spectrum. You remember that Raman is working at 90 degrees, so that the light goes, zoom, and scatters everywhere. So basically, what we used to do in Raman in the old times is that you make a pellet, which is flat, and here comes the laser. Here you have the pellet flat, and then you put it 45 degrees so that it will reflect preferentially towards the detector. I guess all of you have been playing with the sunshine and the light and the watch taking the reflection somewhere over there. Like something like you do these things in classes and the professor is like, ah, ah. Okay, I did that when I was a kid. And it really helped me a lot because the first time I was doing Raman spectra, I was working on this 90 degrees configuration. And then you have to play with the sample, tilt it and orientate it until the light is reflected to the detector that you can hardly see. So you play with it, you make a spectrum, nothing. You move, repeat a spectrum, nothing. And each spectrum was 20 minutes. So it takes a while. So the more you practice on reflecting light, that was good. But nowadays, we are basically working on backscattering, which is basically you illuminate and you collect. That makes things a lot more easy. But Miguel, light scattering is much better on the side. True. But we're using a microscope. We are very close to the area. So anything that scatters is pretty much going to the microscope because the microscope is right there. And then it's very easy because you no longer have to send the reflection to your professor. No. Now all you have to do is like a photography, focus. When it is in the focal plane, that's it. You don't have to orientate, you don't have to tilt, no. Everything is aligned. It's the same direction you illuminate, things go back. And that makes things extremely simple. Conceptually, the design was something easy. It's basically originally you illuminate from the sides, 90 degrees, and then you take the optic to the detector. Now you illuminate from the same direction you collect, so you have some kind of mirror inside, you illuminate, and it goes back like this. So here, you have to control the orientation and many things. Now here, the only thing you have to control is this distance until you are focused, and then everything goes into the detector. How do you do that? Well, you get like some kind of lenses inside the microscope that will do the job of reflecting and being transparent, depending on how the light is coming into. So these kind of things are doable. This is when I was at Lehigh, and probably Sagar has seen those things, the way I was working. So we were using big laser, and we were using this in situ cell where you put the platelet like that, and then you have to orientate. That was an in situ cell where you control the atmosphere, you have made temperature treatments, and then you have to play and you have to orientate and you have to wait 20 minutes to see if the spectrum was made. So I was making a lot of photos with a high exposure time that look great. And actually, Israel has some of these photos in his office, if I'm not mistaken. So I was taking many of these photos because it's very nice to be playing with a laser where you get all this light like this, and it's very nice. But after many days, you get tired. So nowadays, the Raman system looks like this. Light comes from behind, whereas the lasers are behind there. Here you have a beam expander to make them more thicker, homogeneous laser beam. Here you have a mirror, takes the laser into the microscope, and then it goes back. Somehow you get rid of the laser, and only the non-laser, which is Raman, goes into it through the slit. This is a mirror, a grating to disperse the light, and the detector. You don't need a microscope. You can use fiber optic. And in the case of fiber optic, things will look very simple, and then you can basically measure from the tip of this fiber into the sample. So you can go like if you had a microphone, just looking at different samples. And that is very convenient. And you can even put a microscope objective here, even if you don't get the image, to maximize the signal where you measure. But the main problem that we have is that Raman effect is very weak. 1 in 10 million photons will be Raman, but the other 9 million photons will be light scattering. So that means that you have to see at a very little light with a very strong light. Can you see that? No, that's a big problem. This is like something like this. Like trying to look at this candle with the sun behind. You cannot compete. A candle cannot compete with the sun. But basically this is what you're doing in Raman spectroscopy. So what you need is somehow that the light coming from the laser becomes much weaker, and then you can see your Raman signal, because otherwise it is impossible. Now, how do we make that? Well, originally the idea was using several monochromators, because every time you make a monochromator, well, you get the laser and the Raman signal. So, okay, I get the laser out, I open the light, and then I get another laser, and I open the light again. So, but it was very inefficient, and every time that you use a prism, every time you spread the light, you weaken the signal, and the signal is very, very weak. So these kind of solutions were made. Actually, this is like this. So you don't get actually prism anymore. You get a grating, which I will comment now. But the job of the grating is the same, and you have gratings in your house, by the way. You will see it now. And with these gratings, you could more or less separate the laser from the Raman, so that only the Raman goes into the detector, and the laser is just cancel out within the spectrometer. They can even use 3 monochromators, and again it will be the same thing. So basically you have like a concave mirrors that after the grating concentrate the beam, and again you spread the light, but this is a headache. So at some moment in time, early 90s, people came with holographic notch filters, and the holographic notch filter is the closest thing to a magic mirror. You know magic mirrors? Like Snow White and the 7 Dwarfs? You know what a magic mirror is? That reflects something magically. Okay, so what they had here, it was something like that, but it was not magic, it was technology. So what was the magic of this filter? That you make this filter specific for a given laser. For instance, 514 nanometer green laser. Okay, so I have an holographic filter for 514 laser. So you put it in your spectrometer on the way to the microscope. And this notch filter, when you get a green laser, talks to the filter as a wavelength 514, out. And then when it goes to the sample, all the light from the sample comes back, and most of the light that comes back from the sample is 514, because 1 in a million is only Raman. So all of them that go back with wavelength 514, oh, rejected. So this is a mirror to all of them. But if some photon is coming back and the wavelength is different, are you 514? Say, no, I have a longer wavelength. Okay, then you may go. So it's like a magic mirror. So anything that is not the laser will go through. So that something as simple as that will reject the laser within experimental error, and only Raman photons will go into the prism and into the detector. That is very good because you don't have to use several prisms to take away the laser. That means that you are not diluting the signal, so you get the maximum possible signal just because you have a magic filter. At the beginning, they were holographic filters based on proteins that they degrade, but now they are called edge filters, metallic, and they live forever. Or at least for us, they live forever, yeah. And these filters do the same job. So basically, only anything that is different to the laser will go through and gets into the spectrometer. That is very convenient. How good does this filter work? Okay, it will eliminate the laser line plus minus a few wave numbers. Originally, they were eliminating the laser line plus maybe 200 centimeters to the -1. So basically, that means that anything below 200 Raman shift you couldn't see, but 200 and above you could see. Then they improved to 100, 50, and even better. So right now, you can see and you can get very close to elastic scattering. So you can get very close to 0 Raman shift. Of course, 0 Raman shift will never get there because 0 Raman shift is the laser. And basically, this is the way it works. If you don't have a filter at 0 Raman shift, you get 10 million intensity. And here you get your sample. Now, with the notch filter or with the edge filter, you are killing the laser line plus minus 20, 30, 40 Raman shift, which means that you can still to see a spectra beginning at 100, 50, whatever. And from here to there, you can see spectra nicely without the interference from the laser that you have. And this is what we have here. And this is what here makes the frontier. So the laser is in the blue line that goes to the sample, goes back, scatters, collects, goes back, and over here only the Raman goes into the spectrometer and is analyzed. The grating, well, grating is something that basically is like a lot of groups per millimeter. Do you have something in your house that has like a lot of groups per millimeter? Do you have CDs and DVDs? Now, a CD and a DVD has a lot of channels, many, like thousands per millimeter. And actually, if you look at the DVD and you do like that, you see colors. You see a rainbow. You see diffraction of light. This is a grating. So the light of your sample goes like that, and then you get this rainbow. Basically, you are getting all the spectral lines. It's doing the same thing that the classical prism used to do. But the classical prisms, you have to go to the prism, through the prism, so you are losing some photons. In this case, it goes and scatters, so it's much more efficient. Now, the scattering of light will depend. If you have like 600 groups per millimeter, the opening of this rainbow will be a given one. If you have more groups, it will open more. So the more it opens for a given detector, the higher the spectral resolution. Makes sense? Agree? Questions? Panic? Okay, good. So basically, how does an spectrometer work? You will buy a system that has probably several gratings, like 1800 groups per millimeter is a typical one. But what happens? That in the detectors have a given size, they're pretty much standard. So it's either you see this part, or you see this part. So basically, the grating will move so that you select which part you are looking at. The resolution, here you see many things, but of course the resolution is lower. Here you see less things, but with higher resolution. For a given grating, depending on whether the detector is closer or more distant, the spectral resolution will be better or worse. So basically, they are playing with these kind of parameters for the resolution of the system. So here you have from old Oriba system a spectrum of a given sample with the 16 groups per millimeter. So with the 16 groups per millimeter in one shot, you get the whole spectrum from 100 to 3,000-4,000 Raman shifts. So you get everything all the way up to the CH. Now, the quality, the resolution of the spectra is not that high, but you get everything. Now, if you are using like 1,800 groups per millimeter, you only see one part, but with a lot more resolution because you still are using all the same amount of pixels in a more focused area. So you look at the same region, but the detail is much better. Actually, you see like that. Look, for instance, here you see peaks 14, 15, and 16. There appears to be a shoulder there. You see that shoulder? Yeah, appears to be a shoulder. But now with the other grating, this little shoulder is actually another peak, a resolved peak. So you win something, you lose something. But you know, I want everything. I want resolution and I want all the spectral range. So what do? Well, in the spectrometers, basically, okay, you get the low resolution, then you get everything. You get a group photo. Like with the telephone, you make a broad view angle, fine. But then I cannot see your details. Or I make a photo, I make a photo, I make a photo, I make a photo, and I make a photo, and then I can see all of you with many details. But I make a photo, I make a photo, I make a photo, and I make a photo, and then when you connect the photos, things do not match perfectly. Then they came with the telephones with this idea of the panorama, that you make bzzz. So the same CCD is recording everything, synchronized with your movement. Now, you think that this was an idea of the telephones? No, that was used in the Raman spectroscopy. They can do things like the grating is moving continuously, synchronized with the detector. So you can get more resolution and get everything, just the same way that you make a panorama photo with your telephone. So you can play with all these things. And even some people get with a kind of grating called a shell that basically was managing to get the whole spectrum in all the CCD area in one shot. That was very complex, but this company is no longer selling these equipments. But that was nice because you didn't have to move anything. It was getting the whole spectral range in one shot. Raman systems, you have all kinds of sorts, all colors and all shapes. Big ones, small ones, portable ones. So the first one we had was this one. Now we have a newer version of it, but it was the one from René Show. We also have a Perkin-Elmer. Very popular is this Oriba that you have been using. All of them. Now, they come in all colors, all shapes, and all forms. Now you are getting this kind of portable Raman systems that, I mean, it is not in the cell phone, but it's like a small thing connected to the telephone. But this thing you see here, this is also a Raman system. This is from a company called BaseSpec, and they say that they start selling those things for the US government, for the CIA. Then they start selling it to the US Army, and now they are selling it commercially. Of course, the spectral quality and resolution is not very good, but you get peaks with a low resolution, but to identify, given a number of components, whether this is A, B, or C, it will work. And it is working there, and then with the Bluetooth, you read in a telephone whatever is there. But they can in any size. For instance, I don't know if you can imagine the size of this Raman spectrometer, but it is like this. I don't know why they put this photo. It looks like a big rack thing, but it's actually this one. And it has a portable thing there that goes into it, and you focus through the glass into the sample. The glass is transparent to Raman, so you can identify liquids. You go with these portable systems, and these kind of systems are becoming increasingly popular in the past few years. And at the beginning, they were terribly expensive and terribly bad. So if you were buying those, okay, you were a snob. Oh, I have this portable Raman system. That's the question. No, but I have it. Now they are working. Now they are having a good signal, and they can do these kind of measurements. And actually, if the link works, they also have like standards for different kind of applications. Like for instance, you know that in your telephones, they have this IP68, IP64 certification, so that this can go into the water, you can drop it. Okay, now they are having portable Raman system with those certifications that they can go into the water, like here, or you can drop it. And actually, if the video is working, you will see the kind of things they do to a Raman system. Don't do that with our Raman systems, please. So this is a portable Raman system they have. This is a company based in Denmark. And we will probably play with one of those. Okay. It appears it's working now. So they have it connected by Bluetooth to the computer. So the system is basically a little box with an objective. They have a sample attached to the objective, and they're playing with the sample. So the sample is continuously measuring there. Come on, there's people waiting. It's run. Yeah, no, yeah, but so they put it into the water. It's still running. This is a near-infrared laser. Near-infrared, you don't see near-infrared light, but the CCDs do see near-infrared light. But when they are there, they don't see that light. The telephone will see that light. That's why they have also the glasses to protect their eyes. So the system is working fine, and then the system keeps on running without a problem. And they also have a certification for impact and these kind of things. Just one moment, and then I'll quit. Don't do that with my equipment. They drop it, they kick it, they put into the water, they play football, all these things. So really, Raman systems are changing, they're improving a lot, and they are going into very many interesting developments. So the future of Raman, you can see that is certainly unlimited. And these are like these portable ones. You can put them into water, and Raman is good with any excitation line. I told you that. And that is very interesting because another challenge, another advantage, but at the same time another limitation of the Raman system is that it can work at any wavelength. But working at any wavelength, it also has a limitation. You have to read the signal. And when you read the signal, the detector is a CCD like the telephones, better quality, refrigerated, and so on, but it's basically a CCD detector what we use in spectroscopy. The response of a CCD detector is not linear with the wavelength. It is much more sensitive to a given color. In particular, a typical CCD response is like this. At about 500 nanometer, which is green, it has a moderate response. 700 nanometer, which is like red, it has a much better response. 800, which is like near infrared, the response is good but decreasing. And 1000 plus, which is infrared, the response is even weaker. This is a problem because when you are going to the red and infrared, the Raman effect is weaker and the detector becomes blinder and blinder. Over here, this is okay because the detector becomes weaker and weaker, but as you go to the blue, the Raman effect is stronger and stronger. So you get like a stronger Raman effect that compensates the fact that the sensitivity is lower because there are many more Raman photons. If you go to the UV, this detector don't see UV photons, but usually this detector comes with a coating that convert every UV photon into a visible photon and will read without a problem. Now, if you make Raman with infrared, you see nothing, and then they use different kind of technology. Now, the other thing is that you remember that for a given laser, you get the peaks. For instance, at this laser, you get this peak, at this laser, you get these peaks, at this laser, you get this peak, and in this laser, you get these peaks. Okay? So it's basically like a green laser, you get these peaks here. So the system is becoming increasingly sensitive when reading your peaks. With this laser, you get your peaks there, that basically the system will even get a better response in the middle peaks for a spectrum that goes from 0 to 3000 Raman shift, and 3000 is like carbon-hydrogen already. And if you are using a near-infrared, you get these peaks here, but the system is becoming weaker and weaker and weaker. So the way this sample will look to a Raman system with a green, red, or near-infrared laser will look different because it have a peak like this and a peak like that to the green. But these peaks may look like this to the red and may look like that to the near-infrared because the system is becoming increasingly sensitive, goes to the maximum of sensitivity, or is decreasingly sensitive. So the way you are recording the Raman spectrum is not what really happens, is what your detector sees. Now imagine that you want to certify a material, identify it with the Raman bands, position, relative intensity. You have to do something to correct that. There is nothing, well, there was nothing to correct that. We had a European project we coordinated about harmonization of Raman spectra, basically to take account of this and many other things, because when you make a Raman spectrum, which laser you use, it has an effect, you've seen that, because the Raman effect can be stronger or weaker. How you illuminate tells how well you collect things. Well, basically anything is affecting you. The fluorescence will interfere, will change the baseline, the dispersion of the light, the grating, the firmware, the detector. So in the end, when you are making something, things look different, and you know look different because even for a very similar optic with a very similar detector, you take a photo, and I take a photo of the same place, and each telephone will give you the same image, like these two photos here, But you see that they don't look alike exactly the same. With the spectroscopy, things like that happen. And of course, you know, this is the landscape. This is the same landscape, this is the same place, but these little differences in spectroscopy means different positions, different relative intensities, different peak widths, because of very many things associated on how you illuminate, how you acquire, and how you process the signal. And that is a big headache. So what we did in the CHARISMA project, that stands for characterization, harmonization, CHARISMA, that sounds nice. So we were doing like round-robin experiments where round-robin experiments when you get many laboratories doing a given measurement of the same sample as a reference. And then you get the spectra of polyestyrene, which is like a good reference material. And we were looking at something like 10 Raman systems, and at the end of the project we have like 20 plus Raman systems. These are the Raman bands of polyestyrene. As a person, you say, okay, well, it is the same, but you cannot help feeling uneasy that, okay, this peak at 1400 plus is not exactly the same, these peaks are not exactly the same, sometimes there is like a big difference there. So after we do the harmonization, everything becomes much more consistent, not only about the position, about the peak, but about the relative intensity of the peaks. So there are many things that are being improved by doing that. Or here, like for instance, for this other peak, you get a lot of noise around the actual position, and after harmonization, everything is much more consistent. And that is very important when you want to make quantitative analysis, machine-readable files, process automatization. So the kind of demonstration that we did in CHARISMA was, you know that Raman is good for everything. So we demonstrated this harmonization of Raman spectra on one side with the catalysis company on the real-time synthesis of a zeolite with Haldor Topsoe in Denmark. We work also with the Spanish Mint, which makes Euronotes, passports, and other things, and they have a Raman active marker. And with another spin-off company from the CSIC, from our institution, which is an additive that you put in the plastics that scavenges, removes the moisture. By doing that, they avoid liquid water to grow in the surface of raw meat. And by doing that, you avoid bacteria to grow there. So the raw meat with this kind of plastic can last like 50% longer. It can be from 2 to 3 weeks without bacteria. In all these three cases, the active component can be monitored with Raman spectroscopy. So we can monitor how the zeolite is being developing until the final point. In the case of the Spanish Mint, what we do is these Raman active markers that are added to the Euronotes and that are in the passport give a Raman signal that is also used for validation. You're not going to use that on everyday basis, but the secondary high-level control will take advantage of these kind of markers. Document security marker is an amazing universe. They have so many technologies and very high-level advance for the counterfeit. And for the food, this additive that is removing moisture, it's getting saturated. The more saturated it is, the longer a bond becomes. And you know that when a bond becomes longer and longer, the Raman frequency is lower and lower. So you can monitor at what moment this protecting agent is saturated. So the supermarkets can keep this food and they double check in the logistic with the portable Raman system. Okay, this is protected, this is protected, this is protected, this is close to the end of the protection. So all kinds of things can be demonstrated, and everything is to be used through the cloud. And you can be using like a portable Raman system, desktop Raman system, medium, high level, whatever. Everything has to be connected and validated. CHADA mainly stands for characterization data, which is all the files, because the file must have all the information, the spectrometer, the conditions, whatever, all this information. You will see it for Raman, you will see it for infrared, you will see for everything, because in the near future, every data will come with all the metadata associated with the experiment, with the conditions, with the equipment, and with everything. So, well, we have these results in the CHARISMA project, and in the website you can see things. Even we have a video tutorial about good practices in Raman. And everything from CHARISMA is a European project, so it's open access, it's free. The papers we made are over there, are available. And also the tools that have been developed to harmonize the Raman spectra. We have made tools which are reference materials, very simple reference materials, one kind of silicon or one kind of calcite, polyestyrene, and a neon light, just which are used just to calibrate, and software to do that. And the software is open source software, which is on the website, and there is a link to it, and it can be used for free to handle and correct the spectra. Okay, and the final characterization, Panther 30. Okay, then we talk a little bit about the surface chemical probing, and then hopefully today we already start talking about operando, and certainly on Monday. 15, okay, so 20 to 11, we continue here.